So the next topic in this section is going to get into area. And so now the definition for area. The area of a polygon or figure is the measurement of the surface covering the figure. So again, think of like a tablecloth covering a desk or a table or something. How much surface are you covering? And how that's going to be done is we're going to have to first develop a measure of units for area. So to measure the area of an object, we first need a basic unit of area. For example, a 1-inch square has an area of 1 square inch. Now, that seems a little confusing, but in general, they like to use squares as a way to measure area. So here we have an inch by an inch square. So by definition, we can say that the area is equal to 1 square inch. That's the basic building block for area. So anytime you have little tiny squares like that, that's 1 by 1, you have 1 square unit, whatever it is. It might be inches, it might be centimeters, it might be miles, whatever it is. It's going to be square, whatever it is. Now, this is a lot of words to write for area. So mathematicians, they like to make things more simple. So instead of writing it like that in words, we can write it with an exponent. So the exponent has to be on the units, after the units, like this. So whenever you see that exponent of 2, it's a two-dimensional shape that you're looking at. That's why it's there. So this is a two-dimensional shape. Okay, so that's our building block. So now let's see if we can use that to our advantage to find some other areas. So let's look at a rectangle that's 4 centimeters by 3 centimeters. And if we wanted to find the area, we could first look at chopping it up into smaller little blocks like that. So we have all these little blocks, and each one of them is 1 square centimeter all the way through it. So if we wanted to, we could just add up all of those different squares and you get a total of 12. Now that's kind of clunky, but if we look at the 2 dimensions and look at the answer, we can kind of see what the trick is. So all we need to do is just multiply those 2 dimensions, and that will get us to our answer. So multiplying the length and the width will get us the area of a rectangle. So that's our first formula. Area of a rectangle. If we know the length and we know the width, all we have to do is multiply those 2 together. So again, we just have a rectangle, and again, we need the length and the width. And just flat out multiply and you're done. Now, for a square, which is a special type of rectangle, remember, you got the side times the side. So, I mean, technically speaking, you got A equals S times S, but S times S, we can make it more compact if we just make it with an exponent. So this will give you the area of your square. And then for a parallelogram, which is a new shape, we haven't talked about it, but a parallelogram, which we did talk about, but we didn't look at it too in depth. If we wanted to find the area of it, we need to know the base and the height. Now, we got to be a little bit careful about what those dimensions look like in a parallelogram. So let's draw our parallelogram. Now, knowing the lengths of all the sides is not going to help us with finding the area. We need a special dimension in a parallelogram, and that special dimension is right here. And why it's special is because it forms a right angle with one of the sides. So what they usually like to call the B is the base. So the base of the parallelogram is B, and then this dimension here is H, which is the height. So because it forms that right angle, now we can find the area of it. Because remember, we always want to use little squares. So it's kind of hard to put a square in a corner like this. So we need that dimension. And what actually happens is, if we stole this triangle and put it down over here, then it forms a whole rectangle. So that's essentially what they're doing. They're just kind of reconfiguring that parallelogram into a rectangle. So, okay, let's take a look at a couple more. A trapezoid. So we know what a trapezoid looks like. So there's our trapezoid. So now we need some dimensions in here. So we need the parallel bases, B and B. So that's going to be this is going to be B. That'll be big B. And then we need a height again. Well, just like with the parallelogram, we need that right angle relationship. So we're going to do the same sort of trick. And we're going to drop that line down to form a right angle. And there's our height. So this will give us our will get us to our formula of 1/2 h times b plus b. Now, if you're not quite sure how that works, why that's the case, the trick is kind of similar to this, but a little bit different. What they actually do is they make an exact copy of this trapezoid and then they flip it upside down. And when you do that, you're going to have something that looks like this. So look at the entire thing and you can kind of see that we have a parallelogram. So we have the whole parallelogram, but the base in this case is going to be b plus b. Little b plus big B is the whole base. So that's where that comes from. The height is there. And then since we don't want the whole parallelogram, we only want half of it, they chopped it in half. So that's why the half's in there. So that's how that formula's arrived at. And then the last one we're going to look at is for a triangle. We know what triangles look like. And we got the same kind of relationships. We got a height and we got a base. So we got our B down here. We're going to need that right angle again. And you can kind of see that it's really very close. Whoops. It's really very close to a parallelogram, except it's got that 1/2 in there. And the reason why, similar to what we did with the trapezoid, is if we made an exact copy of it and flopped it down next to it, you have a whole parallelogram, but we chopped it in half. So that's where that comes from. Again, you don't have to know where the formula comes from. You just have to know which formula goes with which shape. So keep that in mind. All right, so let's test some of these formulas out and see what we can do. So we got find the total area. So we got a bunch of shapes all just kind of connected together. And so, well, now the one thing that's not in this diagram, which probably should be, is that. So as soon as you make a right angle in one of them, that forces all of these to be right angles. So now we know that we got rectangles and maybe some other shapes in there too. Like in here, we can kind of see that this must be a square, right? So let's break it down bit by bit. So we got our first rectangle here. So what would be the area of that rectangle? What would we have to do? So we got our two dimensions, 3 and 4. So we just have to multiply those. Again, length and width are interchangeable, so you don't need the L to always be the big one. As long as you're multiplying them, you're fine. All right, we got a square next, right? So 1.5 to the second power. Now what about this shape? So we got 5 times 4. That is not correct. And the reason why it's deceiving, but this 4 is only looking at this distance up here. So you got to be careful. If you look over here, there's a 1. That 1 carries over to this part here, so the whole thing is got to be 5. So we got 4 and the 1 gives you the 5. So we actually have another square here. So this is 5 to the second power. And then we do have another rectangle here, so 7 times 1. So that should be all of those individual areas. So now we can do the math and figure out what the total is. So we got 12 here. Excuse me. 1.5 to the second power is 3. You better not say yes. It's going to be 2.25. 1.5 times 1.5 is 2.25. And then we got a 25 here, and then we got 7 there. So looks like we're going to have, looks like 32, 44, 46.25. Now, we didn't have anything with units in this problem, so this is the one time that you're going to be absolved from not having units on your answer. Now, if you wanted to put square units, you could if you want to be really technical, but if there's no units on the problem anywhere, you don't have to have units on your answer. So, all right, let's try another one. Okay, find the area of the two lots. So we got 75 yards, we got 40 yards, and we got 50 yards. You can kind of see we got those two lots that we're trying to look at. Well, if we wanted to try to do something similar to up above, say, okay, we got a, looks like, again, we didn't have it in there, but let's put it in. We got a right angle here, so this is going to be a rectangle. And we can see down here that this is kind of looking like a trapezoid, but it's kind of on its side a little bit. So if we find the area of the rectangle and the trapezoid, we should be good. But the problem is where exactly are we stopping? The 50 yards, it's hard to tell, but the 50 yards is this entire dimension here. And the 75 is this entire dimension. So it's not really telling you where it chops it up on the side. So what we can't really split it into two shapes. But look at the entire shape. The entire shape is a trapezoid. So, and since we know the entire length of this side and the entire length of this side, those are our two parallel bases. So we can use the trapezoid formula once, and that will take care of the entire thing. So, what is our height in this one? What is our h? Well, this 40 yards is that distance between those two bases, and we know it forms a right angle, so that's got to be our h for this problem. Like I said, if you have to turn the whole thing, and look at it that way, so that way it looks more like a trapezoid to you, but it still will work. So just remember that the two bases are always the parallel sides. That's key. So now we can plug in 50 for the one base and 75 for the other one. Now, be careful when you do this. I would say the safest way to do it would be if you want to save the 1/2 for last and take care of all this multiplying and stuff first. Now we can just add that together. And so we got 1/2 of 5,000, which is 2,500. Now the units are in this problem, so we got to make sure we put the right units in our answer. Since it's area, don't forget the exponent on the units. So 2,500 yards squared. So I think we're looking pretty good. Let's take a look at the next one. The area of the outside square in the following figure is 1,200 feet squared. What is the area of the inside square? So the area of the outside is equal to 1,200 feet squared. Square feet. What's the area of the inside? Now, we could tackle this one of two ways. One way would be to say, okay, if I know the area of this whole thing, I could work backwards using the formula, right? So we know the formula for a square is A equals S squared. So we know what the area is, so we could replace that. But that would mean we'd have to find the square root of 1200. Now, if I put the square root of 1200 in here, I get a really nasty number. So I think we might want to try a different route, because once you have that side, then we'd have to cut it in half, because eventually we'd want to find out the length of one of these sides, because then we could use that formula again and figure out this inside area. But again, that's going to be a lot of yucky work. Let me do a little modification. If I put these lines in here, what do we got now? We got one triangle, two triangles, 3, 4, 5, 6, 7, 8 triangles. And all those triangles are the same exact size. So if they're all the same size, and I know the entire area of all 8 of them is going to be 1200, how big is one of those triangles? All I have to do is divide, right? If I take 1200 and divide it by 8, I get 150. And I'll put the units on too. So 150 square feet would be just one of these little triangles. So if I want this inside square, what should I do with that? Yeah. All I have to do is multiply that by 4. And so that's going to give me 600 square feet. So as much as formulas are usually the way to go, sometimes you got to look at alternatives to those formulas, because otherwise you're going to be getting into a lot of messy work. And you can see this process was much, much faster than trying to find square roots and then taking half of them and squaring them, and it was messy. It would work, but it's just a lot, it's going to be a lot more work than doing it a shorter way like this. So, okay, let's try one more and then we'll see what's on the next page. Yeah, we'll stop after this one. Okay. Given a square with side 36 inches, what is the area of the shaded region? Now, this one is kind of nice. So the one thing they gave us is that this is 36 inches. So that means we know this is 36 inches and all the way around is 36 inches. But they want the area of the shaded region. Now the trick to this one is looking at what's not shaded and seeing if we can find that area. So look at the unshaded triangle here. Could we find the area of that? And the answer is yes. Because, let me put a dotted line in here. We know, do we know the length of that dotted line? Sure, right? It's going to be the same 36 inches. So if we want the area of this triangle, we can find it now. We have a formula, we have the height, we have the base. But we still don't know about these unshaded pieces. The trick to this is now we got to look at the square. So we need the area of the square, and then we need to take out the area of the triangle that's not shaded. And that will leave us those shaded pieces. So in general, we can create a formula that looks something like this. So the area of a shaded region is always going to be equal to the area of the outside shape, which in this case is the square, minus the area of the inside shape, which is this triangle that's not shaded. So let's find those pieces. So the area of the square, well, the square is just going to be 36 squared, which I believe is 1296, but let me just double check. Yeah. Okay, so 1296, and let's put our units in there, inches squared. And now we need the area of our triangle, which is a half base times height. And remember, the base and the height are 36. 36 each. So half of 1296, which is 648. So now the last step is to plug those two pieces in. Now this one's special because it turns out to be 648, but sometimes you have weird shapes on the inside that are not going to be such a nice case like this. So, but in general, this is a pretty powerful formula for these shaded problems. So we're going to see some more of those to come. All right, so we'll stop here and we'll see you in the next video.